Welcome to alternating series. Today's a big section, so let's just jump right in with the definition of an alternating series. An alternating series is one that alternates in sign. It can either start with a plus or it can start with a minus. It doesn't matter, but the signs have to alternate. And so all the UNs have to be positive. Let's look at it in a couple of examples. In this first example, the first thing I see is that my UNs are not positive. These are my UNs right here. It's not looking good. Let me show you what can happen when that happens. I've distributed the n to the -1 and the 2, and now let's clean that up. This is -1 to the 2n over 2 to the n equals 1 to infinity. But 2n is always even, so that's simply the sum of 1 over 2 to the n equals 1 to infinity. So that's not alternating at all. All the terms are positive. So that's a big no. Next one doesn't look quite alternating because there are no -1s in there, but let's see what happens. I wrote out the first three terms. Cos pi is -1. So this is, the first term is just -1. The second term is a half. And then the third term is going to be -1/3. And you can see it goes on like that. So we can rewrite that as the sum n equals 1 to infinity of -1 to the n times 1 over n. So that is indeed alternating, yes. And so my u sub n's are 1 over n. So here's the alternating series test. If you have an alternating series, it converges if these three conditions are satisfied. One, the terms un without the minus, just the sequence un goes to 0. All the uns are positive. That just ensures that you have a truly alternating series. And the sequence un is a decreasing sequence. Now, it's okay if the sequence is not decreasing at first. It only needs to be decreasing eventually. And I want to point out, if condition 1 isn't satisfied, then you can't use this test. Stop, abort, and use the divergence test. Okay, condition 3, I want to mention a little bit more about that. When is it obvious that the sequence is decreasing and when is it not? It's going to be obvious if the numerator is fixed and the denominator is increasing. So you won't have to justify a decreasing sequence in those cases. You will have to justify if both the numerator and the denominator are increasing. And we'll do examples of those in a minute. So let's just jump right into the first example, which is called the alternating harmonic series, because it's the harmonic series that alternates. We're going to use the AST, alternating series test, with our u sub n equal to the sequence 1 over n. And you always want to state what un is when you're using the alternating series test. So this is just going to be a series of check marks. Condition 1, limit as n goes to infinity of my UNs, 1 over n, that equals 0. Check. Nothing to show. 2, 1 over n is positive. Check. That's true for all n. Remember, n's 1, 2, 3, 4. N's a positive number. And then 3, the sequence 1 over n is decreasing. No justification necessary. Check. The conclusion is series converges by the AST. Okay, let's look at another one. This is an alternating series, and I'm going to use the alternating series test, and my un will be ln n over n. Condition 1, limit as n goes to infinity of ln n over n is 0. Now, that's a check mark because that's one of the limits you get for free in Theorem 5. However, if you don't remember Theorem 5, or if you're not satisfied with that, you could show that by switching to function notation, the limit as x goes to infinity of ln x over x. By doing that, that allows you to use L'Hopital's rule. So this is equal to, by L'Hoppe, because we have infinity over infinity, the limit as x goes to infinity, the derivative of the top is 1 over x, the derivative of the bottom is 1, that limit is 0, which shows that the limit of the sequence is also 0. So it's check either way. 2, ln n over n, those are going to be positive as soon as n is greater than 1. So that's fine. That's a check mark. And then 3, we have to show that the sequence ln n over n is decreasing. Now that's not obvious because both the numerator and the denominator are increasing. So we're going to have to show that by letting f of x equal ln x over x. And to show a function is decreasing, you want to show that its derivative is negative. So we want to show this. All right, so let's take f prime of x. Now I need the quotient rule. I'm not using L'Hopital's rule. I need good old quotient rule. Derivative of the top is 1 over x multiplied by the bottom minus the top ln x times the derivative of the bottom, which is 1, over the denominator squared. So that's 1 minus ln x over x squared. Now that will be negative as soon as ln x is bigger than 1. So that's going to happen as soon as x is greater than e, because ln of e is 1. So that's fine. E is 2.7. So as soon as our terms, or as soon as n is 3 or more, we'll be fine. So that's a check. So our series converges by the AST. Okay, let's see what happens when condition 1 fails. Here we've got a infinite series. It's alternating. We're going to try the alternating series test with un equal n to the fourth over n to the fourth plus 1. I say try because this will fail. Condition 1 is that the limit of the terms should be 0. Well, I took the limit of the terms, and you can read that computation there, and I got 1. 1 is not 0. So if you read on the previous page, the box for the alternating series test, it says, if this is not satisfied, stop and use the dt. All right, the divergence test is over here in this box. If the limit of the terms is not 0, the series diverges. So now my ANs aren't just the positive part. These are my ANs with the negative sign. I'm going to take the limit as n goes to infinity of my ANs. Now this limit does not exist. And the reason is, without the negative 1 to the n there, the limit is 1. So with the negative 1 to the n, what's happening is the terms are going plus 1, minus 1, plus 1, minus 1. They're bopping back and forth between 1 and negative 1. Well, that limit certainly doesn't exist. So my series diverges by the dt. Okay, let's look at a fascinating result for alternating series. Suppose you want to approximate an alternating series with just the sum of the first n terms. That's the nth partial sum. You don't want to add all the way to infinity because you're feeling a little tired. So how close are you to the actual sum? The difference between the actual sum and your estimate in absolute value is no larger than the first term that you chopped off. Amazing. So let's take a look at that. Okay, here are 2 examples. In this first one, I want to approximate this infinite series by the first 4 terms and know what is the bound on my error. So the first 4 terms are these terms here, and I added them up. That's 5 over 16. The first term I chop off is 1 over 32. That tells me that the error, which is the absolute value between the actual sum and the fourth partial sum, is less than 1 over 32. It's that easy. I encourage you to pause the video. This is a geometric series. Re-index it. You can actually show that this guy converges to 1/3. Okay, let's do another one. This one's more interesting. This one is like, how many terms do you need to get a certain amount of accuracy? So the Leibniz formula is a formula that actually gives you a formula for pi, in this case pi over 4, and here it is right here. How many terms would you need to use if you wanted to approximate pi over 4 with an error of less than 0.005? So according to our error estimation theorem, we need u sub n plus 1 less than 0.005. So first of all, what's un? Un is the terms without the minus. So that's 1 over 2n minus 1. So un plus 1, be careful, you're not just adding a 1 on. This is 1 over 2 n plus 1 minus 1. So that simplifies to 1 over 2n plus 1. So that's your un plus 1. So what we need is that un plus 1, which is 1 over 2n plus 1, should be less than 0.005, which I'm going to write as a fraction, 5 over 1,000. Now, what I want to do is I want to solve for n. So the first thing I'm going to do is flip both sides of this inequality so I have n upstairs. But when you flip both sides of an inequality, you have to change the direction of the inequality. So 2n plus 1 bigger than 1,000 over 5 is 200. Okay, so we're almost there. I'm going to make an arrow and come over here. I've got 2n greater than 199. So n should be bigger than 199 over 2, which is 99.5. So how many terms do I need? I need an integer number of terms. I'm going to need 100 terms. You need to round up, not off. So even if this had been 99.1, you would still need 100 terms. 99 terms would not be enough. Okay, last topic, some definitions and a flowchart. A series converges absolutely if the series of absolute values converges. So that makes good sense. It's intuitive. A series converges conditionally if it actually converges, just not absolutely. And then the absolute convergence test tells us that absolute convergence is the strongest thing. If a series converges absolutely, then it converges. The easiest way to remember what conditional convergence is with the alternating harmonic series. So we showed earlier by the AST that this guy converges. However, if you look at the series of absolute values, you get a P series, you get the harmonic series, and we know that diverges. So that's an example of conditional convergence. Okay, here's a flow chart you can use to determine if a series converges conditionally, absolutely, or diverges. You can use this on your next test. You don't have to memorize this, but let's use this chart to do some problems. So the first one, does the series converge conditionally, absolutely, or diverge? So here's my series. The first thing you want to do in the flow chart, first thing is you want to check for absolute convergence. So take off the -1 to the n and see if you have absolute convergence. So you always want to state what you're doing, and I started this out and I did that. I'm going to check for absolute convergence, and this is the series I'm going to check. Drop the -1 to the n because we're taking the absolute value of the terms. All right, so that series, if I do rule of thumb, it looks like 1 over n to the 5th, which converges. So I want to pick a test that will show me that this series here converges. I'm going to use direct comparison. Now, remember how direct comparison works. You leave off the summation sign and you take the terms, so n cubed over the square root of n to the 16 plus 5. I want to show the series converges, so my inequalities need to go like this. I can drop the plus 5 downstairs, n cubed over the square root of n to the 16. Now, the square root of n to the 16 is n to the 8. So this is n cubed over n to the 8, which finally is 1 over n to the 5th. And that does it. So the series converges absolutely by direct comparison with, now I put my summation back on, the sum n equals 1 to infinity of 1 over n to the 5th. So according to my flow chart, I'm done. Absolute convergence is the strongest you can get. Your series converges absolutely, and it also converges the way it is, and there's no more to do. Okay, now we're going to do an example of conditional convergence. So again, we start out by checking for absolute convergence. So I'm going to check this guy for absolute convergence, and I do the rule of thumb. It looks like a P series, 1 over the square root of n, and that diverges because P is less than 1. So in this case, I'm going to use limit comparison just to shake it up. So I take the limit of the terms I'm given, and I divide by the terms I'm comparing with. But again, I skipped that step and I jumped right to multiplying by the reciprocal. And so this is going to be the limit as n goes to infinity of, I can write that all underneath the square root, n over n plus 1. Divide top and bottom underneath the square root by n. That's the square root of 1 over 1 plus 1 over n, and now take the limit, that's 1. Now, the significance of 1 when you're using limit comparison is that it's not infinity and it's not 0. As long as that condition holds, your series will do whatever you compared it with does. Now, I compared with a divergent series, so my series does not converge absolutely. So I need to keep going on that flow chart. So I'm right here, no. So now I need to check my original series with the AST. So now I'm going to test the original series, and you always want to write down what you're doing. N equals 1 to infinity, -1 to the n, 1 over the square root of n plus 1 with the AST and u sub n equal to 1 over the square root of n plus 1. Now this is going to be really quick, series of check marks. 1. Limit n goes to infinity of my u sub n's is 0. Check. 2. My u sub n's are positive. Check. 3. My u sub n's form a decreasing sequence. Check. Nothing to show. Numerator's fixed, denominator's increasing. So that series converges by the AST. And so when we have convergence using AST, but divergence in terms of absolute convergence, let me just go show you on the flow chart here. So we're on a yes. We're going on that arrow. And so what we've got is conditional convergence. So this guy converges conditionally. I know, it's a lot to keep straight. And that is the end of this section.